Okay, so let's make a start. I'm very happy. First of all, Toda Rabba, David, for agreeing to present on short notice and just before Purim for us. And I want to say just one thing. I was looking at your bio on the IVS website, and I always say to my students, where is the goal is when you have the confluence of many disciplines. So you know, you have electronic, and by here you have opto, bio, and electronic. So David did his studies at UG Northwestern and Weizmann, and he's professor at Weizmann at Bar Ilan also. And he's opto, bio, and electronics. So you have them all, I think, combined together, David. I'm very excited and looking forward to this presentation. And so the format is usually something like 40 minutes or so of speaking, and then questions and answers. And of course, people can ask questions during the talk. And please don't be shy. I know sometimes people want just to ask by the chat. Sometimes it's not so easy to see them, even dare to ask in person. So David, the stage is yours.
Thank you very much. I should warn you, I cannot follow the chat while I'm talking. It's hard enough for me to focus on what I want to say. So this lecture is about something that is a lot of hope for the future. And I came to it because I am involved in sustainable solar cells. So the work deals with what we would like to have in the future, which is gadgets and useful things that can last longer. One way to achieve that is to have them repair or heal themselves. That because every material that is used will ultimately develop defects. It will be damaged. Now you can repair it by putting a bandage on it, but there's also the way of healing, which, as I will emphasize a few times, implies that there is no external material or other energy involved. And you'll see the difference. So this is work that I started quite some while ago with Jean-François Guillemot and Lior Kronik and German colleagues, and later continued with Igor and the people that you see here. So in order to have sustainable resources, and resources generally we view are energy, but it is also materials. And you have to realize that materials require energy and energy requires materials. It requires the non-destructive use of all resources, and then we can have complete sustainability. However, there's this nasty entropy, and therefore in a closed system, we cannot have 100% sustainability. Realize that Earth is partially closed, we have the effect of solar energy. So we try to get as close as possible. And I put here the picture of a book that at least influenced me when I was a grad student in the United States. And this was during my sojourn at Stanford when I saw this book in the shop, and it quite changed my goals as a scientist. So how can we view the role of materials for a sustainable future? One way is take the materials that exist, but make from them the devices in manner that is sufficiently simple so that it will still function well as our devices today, but that it will be less complex in terms of, for example, the materials that are used, the types of materials and elements. And that is also very important for what we're going to do with them after we are through disposal. Another issue, especially in the AliExpress Amazon age, is to rethink the package. And that is worth a separate note, because of the enormous amount of resources that go into that. And then in general, and that's what we'll talk about, or I'll talk about, the 3 R's, which are repair, reuse, recycle. We'll come to that. There are more R's. For example, reclaim is also one. And there's an E, extract, for the materials that we want from the earth. Let's start with biology as a guide, because sustainability can only be defined if we give a time frame. And this comes from a talk on photosynthesis, where you start in the on the femtosecond time scale, the absorption of a photon, and you get all the way to ecology, which will be years, and sometimes it can go farther, eons. So to make sustainability something that is relevant to our society and planet as a place where Homo sapiens lives, time matters. The fact that we can get a cycle of 1 million or 10 million years is not going to help this species of organism. So we can learn from nature, and I will not give a lecture on photosynthesis, but I myself view it as a kind of miracle, as quite a few other things in biology. And that is because it does already use the practice the reuse, recycle, and repair, and it also has some healing. The material, the system, the photosynthetic apparatus, is one that is not very sturdy unless you look at a sequoia tree maybe, but that is generally the non-living part of it. But it uses a lot of repairing and healing. And I'll give you an extreme example. First, I show this picture to make an impression on you, how complicated the photosynthetic apparatus is. But primarily, I show this because somewhere here is a protein that's called the D1 protein. And it is replaced about every half hour to 20 minutes. That costs energy, but that is the way the system can continue to work. Now, that's a very short half-life. If we could do that, if we would have the energy to do that with some of our apparatus, that might be an approach. By the way, there are others that take days, some take months, but this replacement, this energy requiring process, is a very important part in photosynthesis. And as our gadgets and our equipment gets more and more complicated, replacing becomes more and more difficult. The other thing is that the system has built in quite a bit of resilience until it finally goes belly up. And normally that would require a very sturdy, rigid system. But the alternative that nature suggests is efficient repair and healing. In general, we would associate that with organic matter and the sturdy and rigid system with inorganic. And at the end, this last part of the lecture will be on an inorganic system that actually is resilient because of efficient healing. So we have a cross here also. Back to the big 3 R's of conservation and sustainability. They're problematic because recycling is inherently less than 100% efficient. And it's not only because of entropy, it's also because of the practical problems that would require too much energy to overcome, too much to be practical. The reuse is not something that is easily done because the parts that you might want to reuse may already not be the ones that are needed for today's systems or devices. Also, they may be beyond use if they break in a way that gives them a fatal failure. Now, repairing is there, but the repair of everything needs people who can repair and costs energy. And by the way, there are less and less people that can repair. Because yes, in Rehoboth, you still have a few shoemakers, but there are places in Western Europe, cities in Western Europe and in the US, where it's very hard to find a shoemaker. So if we could provide the materials themselves that make up the device with healing ability, that would allow them to last much longer, because we wouldn't have to take them apart to repair them. And the healing that I refer to here implies that the system will do this on its own without external influence. And that then is called generally self-healing. Self-repair is if the system does this without external influence, but with additional matter or energy. Now here's a material that some of you may recognize. It shows both self-repair as well as self-healing. And that's the double helix, DNA. Hydrogen bonds are critical there. And hydrogen bonds are actually one of the main motives in self-healing of polymers. And polymers are the materials that are most often cited as an example of a self-healing material. But there are more options that we'll see. So one way for self-repair, let's go now to that, is that you take the part that is affected and separate it from the rest to retain functionality at the expense of redundancy. Another approach is that you replace the affected part by a new one, and the new one is provided by means that are part of the system when the system is prepared, if you wish, spare parts. And a popular one is microcapsules in complex matter. There is a material that does self-repair already for many hundreds of years, actually thousands of years, and that's concrete. Every type of concrete has some self-repair because the reaction with water and CO2 can give you from calcium oxide that was not hydroxide that had not reacted calcium carbonate. There are other ways of bringing in self-repair, and that is by bacteria, which is very popular, at least in the scientific literature. It's not yet very practical. And there are other ways that you can now buy self-repairing concrete. It's more expensive than normal one, but it will be able to take care of cracks that form. So here is a cartoon and some real pictures of self-healing from a recent review. The idea here is to have capsules with the healing agent as part of the composite material. And when there is a fracture, and the capsule will be one of the things that fractures, the material that has to do the repair will spill out. Another one is what's called microvascular materials, where you have capillaries running through it with the reagent and catalyst for self-repair. And here is an example of an epoxy that is stored in such capillaries, which are green here, for example, in this cartoon. And you have some access because you don't want to run out. That's the healing agent that can then stick, glue together again the fractured part. And here is a cartoon and a picture of self-healing of a polymer, which you cut, get self-healed. And this is what happens in optical pictures, the cut here, and after 24 hours, going through various stages, you have a reasonably healed polymer back. The mechanisms can be physical or chemical. The dominant physical mechanism is one of diffusion of components. There's also an issue of phase separation, which often is found in shape memory. For example, of alloys, nickel alloys, where it's between two crystalline forms, the martensite and the austenite. And in this case, there is diffusion at higher temperatures, while here at lower temperatures. Chemically, you can have, upon fracture, reactive parts that are formed which can rebind, or supramolecular chemistry comes in play because of the localization of the reagents. That is at least one thing that happens in the guest-host chemistry, or the ionic reactions can be strong enough to bring the components together for healing. And there are others. This is a very nice example of self-healing of piezoelectric organic material, and it's this tetrametal bipyrazole. This is the structure. It's broken, healed, broken, healed, broken, healed, broken, healed. And even here, some healing occurs after a very serious fracture. And the reason is that the material is dipolar. It has also, that guides also the hydrogen bonding. The material is made up of a hydrophilic core channel with a hydrophobic shell, which allows for localization of components. And then the dipolar forces bring the two surfaces together after fracturing. So this nice cartoon shows what all can undergo self-healing in electronic materials. And if you look at it, well, there's quite a few: sensors, batteries, supercapacitors, field effect transistors, solar cells. What they have in common is that in every case, the self-healing is done not by the functional material, unless we are talking about these two, but by a polymer that is added to allow self-healing. In other words, the active material itself is not self-healable. And naturally, it's a possibility to go that way, but ideally, we would like the material itself to do that. And use our organic polymers for other purposes.
Quick question.
Yes.
David, if the active material is not self-healing, then you don't lose the functionality, even if the material self-heals, but not the active part of it? I see, for example, transistor or other things like this.
The important thing is that it will, again, bring the parts of the active material that have been affected close enough together so that they can continue to function. That is what generally happens here. So it's very often you bend the material and the polymer will bend, but also bend backwards because it has elasticity that the active material doesn't have. It has its value, no question about it. But it is, in a way, going around the main problem. So are there inorganic electronic materials that can heal or repair themselves? And here's one, and it's a picture I've shown already for quite some time. Right now it's outdated because this is the Hubble telescope. And as you probably know, it's now being replaced by the James Webb. And there are important differences between the two. The Hubble telescope is in low Earth orbit, several hundred kilometers above sea level. The James Webb is way away. It's in, it's a million kilometers away. So that is important because when the Hubble solar cells were replaced the first time and the second time, this is what was seen. And when these were brought back, these solar cells, these are the panels, yeah, generally the largest part of a satellite, at least up till Mars. The people on Earth were very surprised because they had seen the solar cells decrease in efficiency, but that was nothing compared to the damage that they saw. They had, one would have expected damage like this to completely, essentially finish the possibility of the solar cell to work. That was not the case. And the answer was that these cells, which were silicon cells then, they had the resilience because there was a kind of self-repair going on. And the self-repair I'll tell you about in a minute. But first, for self-repairing electronic materials, the routes that have been explored already are like for all materials, redundancy, to separate the part that is not working from the rest. That is an approach, for example, that was taken by Tesla in his early cars, where they had a large number of very small batteries with electronics that could sense which battery was losing function, and then the circuit was guided around it. But also here, and this is again the solar cell, hit by a meteorite, and the ones that you can see are only a small part of what goes on there. It is not going belly up because it's in low Earth orbit. And in low Earth orbit, there's still oxygen, and these were silicon cells. And then you get silicon oxide, which essentially forms a skin and allows the material, the cell, to continue to work. With the new solar cells, there has to be better protection because they are much more efficient, and they are generally 3-5 based solar cells. So the Webb telescope has a triple junction 3-5 solar cell. So this is a nice example of an unintended design advantage. And we would like to have, we would like to get to design that we do intend. An exception of healing that confirms the rule that generally there is no self-healing in inorganics is the radiation resistance of indium gallium phosphide. And it's known that indium phosphide is what's called radiation hard, also for high energy radiation. And the possible reason for it, I haven't found anything more up to date, is that phosphorus is displaced from its normal lattice side by the high energy photon, which then forms a so-called Frankel pair, a vacancy and an electron, and an interstitial, which will move back because they never move anywhere far away from each other, farther away than a few angstroms, which is because of the very rigid lattice of the material. Now, we would like all our electronic and optoelectronic devices, which includes these kind of materials for these kind of purposes, to be sustainable. But the problem is that when they are functional, they work out of equilibrium. And that is naturally a situation where you can get parasitic processes. And that is what makes them much more vulnerable than if they would just sit there in thermodynamic equilibrium and do nothing. But then it wouldn't be very useful for us. So the material degradation that occurs because of their functioning can lead to complete breakdown, and then you get to the problem of disposal that I talked about already. How does that material degradation come about? And we'll talk about that in a minute, where the goal is that we would like to get to design principles for optoelectronic materials that allow self-healing, and I'll give you two at the very end if you stick with me. So I'll focus on structurally ordered materials. There's a vast class of disordered materials, disordered inorganic materials also, but I will not deal with those. So why do they break down? The degradation is due in such materials to the formation and then the accumulation of imperfections, of defects where there is a deviation from the structural order. And these defects can then coalesce, and this will finally lead to breakdown. Now, the mechanisms that can fight this, if because of a coalescence of defects, you will get stresses, local stresses, which the material can adapt to in order to minimize its effect. If, because of more and more defects being formed, you get higher dimensional defects, you'll get a crack. If the crack can be blocked by a reorganization of the material. And this happens in certain ceramics, which have very high concentrations of point defects. And I'll, in a minute, define point defects. There's also a possibility to have defects form, but that the original material has a way to help these defects recombine to annihilate each other, like an interstitial and a vacancy. And other ways to get back to the original state, which was the thermodynamically stable one before it was active, so that once again, when, for example, voltage will be applied, light will shine, pressure will be applied, the material can be as if new to start with. So defects. We have volume defects, which are holes, voids, cracks. Some vibrations in a way are, if they're too strong. Then surface and interfaces defects take into account that the surface is a defect for a structurally ordered material, and actually for any material because of the difference in the surrounding environment in terms of atoms, of the surface atoms and the others. Then there are line defects, dislocations. You have seen them if you have eaten maize, tiras. And in an ordered material, you'll have them also. And they can lead to cracks unless they're stopped. And these line defects generally come about because of an accumulation of point defects, 0 dimension. So these can be a missing atom, an atom that is in between the atoms that are in their normal place, in an otherwise unoccupied place in the lattice. There can be anti-site effects. A sits on the, not on the A side, but on the B side, and so on, and impurities. And these are very important because these are the ones that ultimately dope your material. If you're a semiconductor or an optical material, and in many of those, this type of doping is critical for the functionality. Now, self-healing inorganics have been known for a while. It was known that certain type of solar cells was experimental solar cells at the time was particularly resistant to radiation or radiation hard, and that's why they were studied originally for space. This was explained by Jean-François Liot, Hans Werner, and me in the late 90s for this material, which is nowadays a commercial solar cell material. It has a few % of the market. It looks like that in a cross-section, a false color cross-section, where this is the heart of the material. And it's a polycrystalline material, which one would expect, and originally it was argued, it cannot be stable because it has lots of different elements in it. And look at the mass of making a solar cell with it, or for that matter, any device, considering the other option, which is silicon. Turned out to be the other way around. It self-heals, and this was mainly studied for copper in the selenite parent compound for what is now the commercial material, because copper is a little bit mobile at room temperature in this material. That is something that had escaped attention because in semiconductor science, which is silicon science, copper is something you have to keep out of the semiconductor. And the industry made a huge effort when they moved from aluminum to copper conductors in the circuits to keep the copper safely away from the silicon. So this was found to be, and it's actually reasonable because in this material, the weakest bonds are the ones between copper and selenium. And that's where most highest probability is for defect formation. But this same copper mobility then gives a chance to thermodynamics, because I have now formed a defect, the system is out of equilibrium, it's in a higher energy state, and by giving the copper and copper-related defects a chance to move, they can move back in order to get to the lower energy state. And that is what happens there and gives you defect healing. And so here is some cartoon to show you have a material with one vacancy. Why will there be vacancies or interstitials? Because that is how this material is doped and active as a semiconductor and therefore as a solar cell. Radiation will kick an atom from its normal place. This is supposed to be the copper. And yeah, there's a mistake here. This should be copper and this should be indium, sorry. Then there is migration. And the atom moves and finds itself finally a lattice position that is empty. And now I have essentially the same situation back, except that the vacancy that was here is now here. And if the material is sufficiently dilute in terms of defects, that will give it back the original optoelectronic properties. So the radiation resilience of copper and gallium selenide, in contrast to that of indium gallium phosphide, stems from its ability to dynamically fix damage rather than withstand them statically. And that is one principle that we will finally use. Now, even earlier, high energy radiation detectors were made by taking silicon and driving lithium into it. Why? Because in order to have a good radiation detector, you want as insulating a material as possible. And it turns out that if you drive lithium into silicon, it will take care of some residual defects that cause undesirable doping and therefore make it more insulating. This was known for a long time, since the 60s. And then it turned out that there was some adventitious process going on, because doing this in a uniform manner is very difficult. But it turned out that if there is some inhomogeneity, the resulting difference in electrical potential will cause an electric field that will essentially redistribute the excess lithium or the deficit of lithium. Okay. There are other thermodynamically driven heating processes, and one is electrochromics, known from tungsten trioxide, and the other one that's illustrated here is the light-emitting electrochemical cell, where you have a uniform active medium. And then when you don't apply a potential difference, when you apply the potential difference, because there are ions in this polymeric matrix, you get a separation. This becomes P, this becomes N. Now, current is driven through here, and you get an emission, which gives light emission. The moment you take away the voltage, it goes back to the status quo ante. And that happens in real life with a material like polyphenylene and vinylene with polyethylene oxide, where the active material is the lithium ion, and the generally halide anion, chloride. So we'd like to be able to use self-healing for lots of devices. And what we have seen up to now leaves us with a very limited choice. And then there was the return of the halide perovskites, which I will now talk about because it opened new windows, also for self-healing. And it turns out that self-healing is critical in this material. So you can grow very beautiful crystals, and you can grow them at low temperature, which immediately raises the specter of stability, because everything happens not at high temperature and then you cool, which suggests that you have a strong high activation energy for any change. Well, and then it gets weirder, because if you investigate these materials, you find that they have exquisite average order. You see that in diffraction, very high quality. So there is negligible static disorder. even though they can be made at room temperature. But at the same time, there's plenty of dynamic disorder, which leads to the expression that these are dynamically warped materials because they are fluctuating, but around a very well-defined center. So there's evidence for this dynamic disorder. This comes from my colleague Lior. And the first one came from X-ray neutron diffraction, which showed very large thermal ellipsoids for the halides. This is the iodide, chloride, bromide, and chloride. And these are materials with lead, which is a heavy nucleus, and it is not moving or very little compared to the halides. And in between, in this case, there is an organic, which is generally highly disordered. So one consequence that we argued from this dynamic disorder is that the lattice behaves as a Boojum for defects. A Boojum is something that makes other things disappear. And that gives rise to the high optoelectronic quality, as I will argue in a minute. But before that, there's this issue about stability. So if everything or so many things are moving there, how can this material be stable? For that, we first look at how it's possible to grow them at low temperature. And if you do the experiments, you find that for the formation from the binaries, which is the least energy expensive one, you find a very low free energy of formation plus activation energy. It's 200 millielectron volts. Other people have done the calorimetry, which is very difficult. And the consensus is that there is about 100 millielectron volt free energy that stabilizes the material. And the stabilization is because of the entropy, which can directly be related to the high dynamic disorder. So with this small free energy, it shouldn't be very sturdy. And that leads then to the question of not only the stability, but there should be lots and lots of defects there. But at the same time, they work as high energy radiation detectors. And high energy radiation detectors, they get beaten more than many simple solar cells. They should be sturdy. You see data for a gamma ray detector with methylammonium lead bromide and a cartoon where the authors are trying to figure out what the hell is happening. Their results are very nice. And in the abstract, they even come very close to what is the reason. They say radiation tolerance stems from the intrinsic structural plasticity. That gets pretty close, although fast ion migration may not be what is the reason. And then in the text, they're a little bit more modest, and they say, we don't know. But the data are there. So what is the story here? Now, let's go back for a minute to some simple thermodynamics. Defects in a material will increase the configurational entropy. So here we have the energy of the system and the number of defects. And the enthalpy goes linear with the number of defects, where this is the enthalpy of formation. However, if I add the defect, I get a very rapid drop because the entropy increases a lot. Many possibilities to put the defects. And that saturates at the point. And that means there's a minimum for the free energy of the system. And that is minimum gives me the equilibrium density of defects. And that is a density that is thermodynamically dictated. Generally, we don't have to worry about it because our materials have defects way orders of magnitude above it. The density depends on the temperature and on the enthalpy of formation. The normal situation is that I have a free energy for decomposition of the material that is way above the formation, the enthalpy of formation of the defects. So I can have lots of defects until the material decomposes. In the case of the halide perovskites, especially this one and the bromide, that is not something that holds because we have the free energy of formation plus activation energy that is less than the formation of the enthalpy of formation of the defect. And that leads to a situation where I get very low defect densities because I get close to the thermodynamic limit, 10 to the 10 per cubic centimeters. And polycrystalline films, which have surfaces which are defects, it's several orders of magnitude higher. But all of these are very low. Now, it's not to say that I cannot get gallium arsenide or silicon that way. It's just that there's no way I can do that from room temperature in a beaker and an Erlenmeyer. So if I can test, by the way, this idea by taking a material that I can make both at room temperature and at higher temperature and see if there's a difference in the density of defects. And this was done because these are crystals from this material, cesium lead bromide, grown from solution, low temperature, 50 degrees, melt grown, 600 degrees. And you have to go, in this case, to slow cooling to get back to the orthorhombic phase from cubic. And if you do that, you find that the defect densities that have been measured by different groups independently are orders of magnitude different. It's about 4 to 5 orders of magnitude difference at least. It tells you that kinetics matter. Also for the stability of a material, how far it can be sustainable. But we saw that already in the beginning when we talked about that. Timescales matter. Here's another example about kinetics. I can make this material from the binaries by just grinding them together. And several groups have been doing this, and they have had very nice results by making thin films with the material that results from that. Now, this is not new. Tribochemistry, mechanochemistry is well known, but not with these kinds of materials. By the way, people did it for copper indium selenide. And they found that only when they're nanoparticles can they get complete reaction. Otherwise, you only get a shell to react, and the rest is not reacting. And that's because kinetics matter. There's another thing, though, here is you do this process, and there should be loads of defects because it's a mechanical pressure-induced process. Where are the defects? And it turns out that this material has intrinsic self-healing, these materials, which we discovered by 2-photon confocal microscopy. And this shows you what you do. You take a wavelength that is not absorbed. You then focus it inside the material where a 2-photon process takes place. So you get now a photon that is absorbed, in this case for this material, and you get photoluminescence. So you can also tell what's happening inside the material. And when you look at the photoluminescence intensity, this is the background. Now you give a pulse, a very strong pulse to cause damage. And these materials react differently, but you can see for all of them damage. And then you see how quickly they change. So this is also shown in this movie, except for the cesium. And there's a reason for it, which I will not go into now. Furthermore, they showed that if you purposely fracture them, as was done by this group from Brown, yes, for thin films, by bending, you get a crack, and now you can compress and you get it back, or you can heat and you can get it back. And they showed this very nicely in X-ray diffraction, where you can measure residual stress. And as synthesized, cracked, and after, in this case, 1 minute, in this case, 10 minutes for thermal, you get back your residual stress of the original system. Because once it's fractured, stress is released. And then here's a demonstration from our lab. This is from the Bar Ilan lab. You take a crystal, you cleave it carefully, then you put the two parts together under light pressure. You keep them there for a month in an inert atmosphere, and you see they stick. You can see it here. And now in this movie, you can see the plane where there was the crack, but they are stuck together. So towards the end, we have some mechanisms that we now know for electronic materials to self-heal and therefore to increase significantly their sustainability. One is that chemical reactions should be made easy to correct for the damage that is done. This is aided by a dynamic lattice and, very important, by product localization. You don't want the product of the damage, of the reaction that caused damage, to diffuse away, because then it won't happen. And we showed that. And the other one, which is the earlier one, is that the defect can migrate. And that is aided by a rigid lattice, which should not be too close packed, not too dense, so that this migration is possible. And both of these, and they may not be the only ones, have implications for optoelectronics made with these materials. The challenge in materials research for the future is to identify and to find more principles for active self-healing, because that is the approach that is most likely to find favor in eyes of the manufacturers, because it doesn't force them to make the manufacturing process more complicated. And so you have passive repair, where you put in something that can do the repair, and up to a point, then as long as there is repair material available, the material will withstand the external damaging influence until it's gone. And then there's the active one, where you can energize your corrective material. For example, by applying external energy. What we've shown here is that it's possible also to let thermodynamics do the job. And that is probably a very good way to do it for inorganic materials, and not only for optoelectronics, but also for energy conversion and storage, where I think it might be more difficult than for optoelectronics. So, and naturally, to show you that I'm a good citizen, yes, I can argue that doing this will at least affect several of the goals for sustainable development that have been set. Thank you for your attention, and you can ask questions, and if I have, I'll give you answers.
Thank you, David. Awesome presentation. I love the material science content that is in there. So now questions. Anybody has questions for Professor Cahen?
Yeah, I have a question. David, so when you talked about the repair in the hybrid perovskites, the discussion was largely couched around, I would say, the microscopic structure, the lattice, the ion migration, but it was shown in materials which either ground together or thin films which have a lot of grain boundaries and a lot of defects, a lot of surface. So what about those other, I say, largely somewhat more macroscopic characteristics of the structure? How do they play into that repair process?
Which parts? The grain boundaries, you mean?
For instance, grain boundary surfaces.
The grain boundaries are defects, like any surface. So it is my opinion that the defect densities of polycrystalline thin films are completely dominated by defects at surfaces. And that is further supported by results on nanocrystals. If they have been passivated chemically carefully, you can get quantum efficiency for photoluminescence that cannot be distinguished from 100%. So if the surface is taken out as a possible source of defects, then you come back to your atomistic picture that I have shown. And the cracks, why can the cracks be healed? Because the lattice is flipping and flopping, and this allows bonds to be remade. But only those bonds where the damaged products have not moved far away from the locus of damage. I don't know if that answers all of your question, but at least the grain boundary then.
Okay, thank you.
Other questions?
דוד, אני רוצה לשאול אותך שאלה. I want to ask you a question, David. I sent a chat. In the passive rehealing of materials that you showed in the beginning of your talk, you actually incorporate in the material several components that are released with time.
Yep.
But these components actually weaken the material, weaken the matrix, aren't they? or they hamper somehow the mechanical properties of the materials?
In my view, they do, yes, but it is the practice generally in polymeric materials, where you may have more leeway. I think the nicer example, which is an unintentional example again, is that of concrete.
Yes.
That depending on the source of concrete,
Yes.
and the Roman concrete apparently is very good in that you get strengthening over the years.
Yes, yes. But that's because you have CO2 in the air.
That's right. That's right. That's right. Yeah. But yes, I wouldn't recommend it for a material that has to have, let's say, a given bending radius or something like that, because you're going to affect it. Yeah.
Other questions? Well, if not, well, David, thank you. It was an awesome presentation, very amazing topic, and I think it kind of lit like the book of Limits to Growth that inspired you. Now a few lights may start coming out in many of us on the way that we design or synthesize our products. Toda rabba. Thank you very much. Purim Sameach, and for the next presentation that we have on this series of big topics from top scientists. Toda rabba. Thank you.
Thank you.
Toda rabba.